All right, welcome back. Good morning, good afternoon. This is our course on analysis and design of rigid pavements. In this course, we started out in module 1, which was more of an introduction. But in the introduction, I pointed out there are different types of rigid pavements, namely JPCP, jointed plain concrete pavements, CRCP, continuously reinforced concrete pavements, JRCP, jointed reinforced concrete pavements, and PCP, pre-stressed concrete pavements. And I pointed out that primarily in this series of lectures, we are going to focus on JPCP. CRCP is generally analyzed as a small variation of JPCP, so we'll have a little addendum to that once in a while. JRCP, and PCP, JRCP is not used that much, and PCP is a very specialized application which is also not used all that much, so we won't talk about it in these lectures. So, module 1 was more of an introduction. Now, in the previous lecture, we began module 2. In module 2, we started looking at how do we analyze rigid pavements, by which I mean JPCP. How do we analyze them using classical methods? As I pointed out, when I say classical methods, it basically means without a computer. So some kind of nice closed form solution which you can write down on a piece of paper, which you can easily calculate in Excel. That's what we mean by classical methods. As we shall see going forward in several lectures from now, these classical methods have a variety of shortcomings and a variety of simplifications. And that's why numerical methods, the finite element method, was used in pavement analysis, rigid pavement analysis, in order to overcome those shortcomings. But that is approximately around 20 to 25 years old as a history. But the classical analysis of rigid pavements stretches back to over 100 years ago. So in module 2, we will look at some of those classical analysis methods, and then we will start building on top of it in module 3. So in the previous lecture, which was lecture 5, I introduced you to plate theory. I explained that you could use layered elastic analysis to analyze flexible rigid pavements. Now, LEA is used to analyze flexible pavements, and one of the basic assumptions in LEA is in the horizontal direction, the slab or the structure is of an infinite dimension relative to the thicknesses. Mathematically, R tends to 0, where R is in the horizontal direction. In rigid pavements, what we saw is the problem with that assumption is that JPCP consists of a discrete set of slabs which have a finite length and a finite width, typically 3.5 to 4.5 meters. Now, while that is certainly much larger than the thickness, it is not as large as, say, a flexible pavement. And so, if we want to take into account that we have these finite size slabs and we don't have an infinite size slab, then layered elastic analysis no longer works. As it turns out, and that's something we'll look at today, the presence of that joint or the presence of the finite size slab actually makes a very big difference to the stress magnitude. So if we ignored that fact and we used layered elastic analysis, we would actually significantly end up underestimating the maximum stresses, and therefore our designs would be highly inaccurate. And consequently, we need to take these joints or these finite size of the slabs into account. And for that, in the previous lecture, we derived the celebrated equation, which is the Sophie-Germain equation, to which we added some more information related to the subgrade, and we finally got the governing equation of rigid pavements. So in today's lecture, what we're going to do is we'll have a quick recap of that governing equation. I'll define the different terms in it again briefly. But then the main agenda for today's lecture is to see some solutions of those equations. Now, as I mentioned in the previous lecture, the equation is quite complicated as such, so it's not trivial to get the solutions. Fortunately, a very, very smart gentleman, Dr. Westergaard, actually came up with certain solutions over 100 years ago. So in today's lecture, we are going to see those solutions and we'll see a solved example. What I mainly want to show you is depending on where we place the stress, so whether we place it close to the edge, whether we place it at the middle of the slab, whether we place it at a corner, we actually end up getting different solutions. And then the stresses are different at each of those locations for the same slab, for the same load. And what I want to show at the end of today's lecture is under what loading configuration do we get the maximum stress. Okay, so let's recall from the previous slab our equation for plate theory. So the Sophie-Germain equation, which I derived last time, basically told us that d del power 4w is equal to minus q. This is the governing equation for a plate. As a reminder, a plate is a special type of structure, or rather, we are looking at Kirchhoff-Luff plates, so medium thick plates. So, a medium thick plate is a special type of structure which, in addition to being linear elastic, isotropic, etc., it follows two additional assumptions which are not made in general layered elastic analysis. Those assumptions being that we do not admit shear strains. So, if this is a cross section of the plate which undergoes pure bending and loading is only allowed in the transverse direction, then the two additional assumptions we make is firstly that all the our shear is going to be in the form of bending. So if I have a cross section and I draw the stress along this cross section, then I'm going to have some shear and some stress which is along this longitudinal direction, but it is not along the vertical or the transverse direction. So we do not admit shear strains. That's one assumption. And the second assumption is that we have a particular plane which is called a neutral plane. At the neutral plane, the stresses are always assumed to be zero. And remember, we're talking about plain concrete slabs over here. These do not have any internal reinforcements. We're not talking about reinforced concrete, which is a separate theory by itself. So we have these plain slabs, and then we have a neutral plane. At the neutral plane, stress always remains zero. In the unloaded condition, if we have any plane which is perpendicular to the neutral plane, that means the angle between the neutral plane and our arbitrary plane is 90 degrees, then after bending, if the plate bends as I'm drawing over here, if the plate bends and we draw the same cross section, the same plane, then that angle continues to be 90 degrees. So planes which were perpendicular to the neutral plane before bending continue to remain plane after bending. It turns out that this particular constraint, we call this a kinematic constraint. When we apply the kinematic constraint, it actually simplifies a fair amount of our analysis. And what we ultimately get is this equation, which is the Sophie-Germain equation. It tells us that if we apply an external transverse load Q, then our displacement in this plate is going to be related to a fourth order equation, which sometimes we also call the biharmonic equation. All the information related to the elastic properties of the slab, namely the elastic modulus and the Poisson's ratio, as well as, and this is important, as well as all the effects through the thickness of the slab, which is the depth, which is H, which is the thickness, all the effects through the depth and the thickness of the slab are going to be contained in this single one term D, which is calculated as EH cubed divided by 12 into 1 minus nu square. We did the derivation for this in the previous lecture. Please go back to it and have a look at it if you're unclear where this comes from. But this plate stiffness contains complete information, of course, about the elastic properties, E and nu. It also contains complete information about how the plate is behaving through the thickness. Remember, keep in mind, we make the assumption that no shear strains are admitted, which means that if I have a slab which is bending thus, and relative to its original position, if I pick a point on the slab and I calculate its displacement W, then relative to their original position, any point through the thickness is going to have the same displacement. In particular, what that means is the displacement on the top surface and the displacement on the bottom surface at the same horizontal point is going to be the same. So this W, which is the displacement, is a function only of x comma y and not a function of z. That is a constraint which comes in because we assume that no shear strains are admitted. And that's a pretty important assumption which we make that simplifies our equation quite a lot. If you think about it, we actually are solving a three-dimensional object, a plate. So three-dimensional object, we should have, in our Cartesian coordinate system, we should have three dimensions, x, y, and z. But because we are making this assumption about what's happening in the z direction, that we are not allowing any relative displacement or any shear strain along the z direction, the effects of whatever is happening in the z direction collapses into this one term, which is the plate stiffness. Everything collapses into the plate stiffness, and now we have an equation where the derivatives are with respect to only x and y, not with respect to z. That is a pretty startling difference. It actually makes a very large difference to how we solve these equations using numerical methods, namely the finite element method. We'll come to that several lectures from now. Anyway, one addition which we made to the Sophie-Germain equation, so Sophie-Germain equation only had this term, which is d into del power 4w. We assume that the JPCP, in addition to the slab satisfying the medium thick plate theory, which is the Sophie-Germain equation, in addition to satisfying this, we assume that the plate is actually sitting on a bed of springs. So we model the subgrade as what we call a Winkler foundation or a dense liquid foundation. And what that basically tells us is that the stress is going to be proportional to the displacement. So as the pavement or as the slab undergoes some displacement, it pushes against the slab. The slab in turn is going to return some reaction, whose stress is going to be equal to Kw. So when we make that assumption in our force balance, we just get an additional term, which is Kw, and we just add it to the left-hand side over here. So this equation then is the modified Sophie-Germain equation with the assumption of a Winkler foundation, and this becomes our governing equation for JPCP pavements. So we saw this in the past, and we derived this in the previous lecture. The question is, it's well and good to have a differential equation. How do we solve it? So one thing to understand when we're solving it, the question is as follows. If we could somehow, if given some loading Q, if given the plate properties D, given the subgrade properties K, can we calculate W? That's something we have to answer. But generally, we are not really interested in the displacement. It's good to calculate it, but that's not what we are interested in as civil engineers. What we are actually interested in is the stress. But the question arises then, which stress? So again, let's look at a cross-section. If this cross-section is under some loading and it undergoes flexure, and we take any cross-section and we plot the stresses, what we will get is this is going to be the neutral plane. So at the neutral plane, stress is going to be 0. So I'm here plotting stress, and this line represents stress is equal to 0. We will have some amount of stress above the neutral plane, and then we will have an equal magnitude stress but opposite in sign below the neutral plane. So one assumption which we're going to make here is, in our calculations, we are going to assume that positive stress corresponds to tension. We will explain why in a second. But we assume that positive stress is equal to tension. So if I say this is my positive direction and I have some sigma t over here, then I'm going to have an equal magnitude stress at the bottom, sigma c. That's because our cross-section has to be in equilibrium. So what I have is sigma t is going to be equal to minus of sigma c. So at the same cross-section, if my top surface is in tension, then my bottom surface is necessarily going to be at compression, and vice versa. So that's something that we have to understand. We are particularly interested in faces which are in tension, and we'll see a little bit more of that on why that is the case in a couple of slides. But first, what I want to do is I want to take the Sophie-Germain equation with the subgrade correction added in, and I want to do a little bit of algebra on it to explain what exactly is going on in the equation. So again, the original equation was d into del power 4w plus kw is equal to minus q. Again, Sophie-Germain was this component, and having the Winkler foundation was this component. All right, what I can do easily is I'll just divide both sides out by this term d, which is our plate stiffness. So when I divide it out, I get this equation over here. Let's consider this term over here, del power 4w. Now, del power 4w, as I had shown 2 slides ago, del power 4w is basically this operator, which I've highlighted over here. Let me just look at the first term of this. So the first term of this is going to be del power 4w divided by del x power 4. Let's do a dimensional analysis of this. So in a dimensional analysis, what we find is that the numerator is based. So we can rewrite this as this is approximately, in a dimensional sense, this is delta w divided by delta x power 4. Now, delta w is going to have a dimension of length, and del x power 4 has some dimension of length raised to the power of 4. So overall, we see that this overall term over here, del power 4w, is going to have this dimension, which is length divided by length to the power of 4. Perhaps all of you remember back from probably 11th class or high school, when you study dimensional analysis, you learn something called dimensional homogeneity. That is, every term in the equation has to have the same dimensions. So if our del power 4 term over here has these dimensions of L divided by L power 4, then this term we have in the middle, K divided by D into W, should also have the same dimensions. Now, what we note is that this W still has the dimensions of L. So what we are left with is that K to the power K divided by D has to have the dimensions of L to the power of minus 4. Now, you can also verify this. Remember, K power D is basically, this K divided by D is going to be equal to K divided by EH cube, and this is 12K into 1 minus nu square. You can verify that this is actually correct, that this K power D does have dimensions of length to the power of minus 4. Again, that is necessarily true, and it is correct if you just check out the units. It is true and it's correct because of dimensional homogeneity. I can define the following. Let me define a term L. And L, I'm going to define firstly a term L power minus 4. This is a small L. Small L power minus 4, I'm simply going to define as K over D. So I'm just applying a symbol over here called L power minus 4. This particular symbol turns out to be extremely important. It tells you a lot about the relative behavior. It tells you the relative behavior of the slab with respect to the subgrade. So it's the plate stiffness to the slab stiffness raised to the power of 4. This term is then called the radius of relative stiffness. This is formally, if you actually work out the mathematics, this is the formula for the radius of relative stiffness. It's an extremely important formula. It's a very, very basic term. You will find this radius of relative stiffness coming back again and again when you look at the analysis of rigid pavements. So it's very important, firstly, for you to be able to calculate it, for you to know the formula, and to keep in mind that it has a dimension of length. So its units are meters, millimeters. Generally, we take it as millimeters. So you should know the units and you should know how to calculate it. Keep in mind, this is a fourth root. So don't accidentally take this as square root. It's a common mistake that students make, that they end up calculating square root, mostly out of habit. So this is the fourth root of this EH cube divided by 12 into 1 minus nu square K. There is a little bit more thing to keep in mind while calculating this, that is to take care of unit consistency. We'll talk about that when we do an example. Okay, so again, this particular term is called the radius of relative stiffness. So let's break down those terms. Radius. All you should understand from the term radius that it is some type of a length scale. The reason it's called radius, as we shall see, this term radius of relative stiffness was actually given by a celebrated scientist named Professor H.M. Westergaard. And when he was trying to solve this Sophie-Germain equation for plates, which is with the addition of the subgrade. So when he was solving it, we won't go into a lot of details, but we will see some of this in subsequent slides. When he was solving it for a circular load. So and that was basically because the mathematics was relatively easy if you assume some type of circular coordinate system or radial coordinate system. So he was trying to solve it for a circular load. Obviously, in a circle, then what do we call a length scale of a circle? It's a radius. A radius is sort of a typical characteristic length scale of a circle, from where you can then derive area and you can derive circumference, etc. So that's why, because he had a particular term, which was this L, and it had the units of length, he decided to say that this was a radius. Relative stiffness, because as I showed previously, this is basically the fourth root of D over K. So this is the stiffness of the plate. This is the stiffness of the subgrade. So this is basically, it's not a ratio because it's not unitless, but it's some type of fraction which shows the relative stiffness of the plate with respect to the subgrade, and hence the term relative stiffness. It's some sort of plate stiffness to subgrade stiffness, keeping in mind that these are not the same stiffnesses mathematically. And hence this particular term got the name the radius of relative stiffness. As I mentioned, it's an extremely important parameter in the analysis of plates, and first of all, we need to be able to calculate it. So we'll do a quick calculation in a couple of examples in today's lecture. We need to be able to calculate it, but more importantly, we need to keep in mind where it comes from. It's not a term which comes from nowhere. It simply comes from taking the Sophie-Germain equation and adding this correction factor for the subgrade, for the Winkler foundation subgrade, and then doing a dimensional analysis on the differential equation. That's where we get this term from. Okay, so I mentioned previously that there is a celebrated scientist, H.M. Westergaard. So he was the first to ask the question, how do we solve this plate equation? It's well and good that we have the differential equation, which again is d del power 4w plus kw is equal to minus q. It's well and good that we have this equation, but then our question is, how are we going to solve this equation? Now, keep in mind that he asked this question in the 1920s. There were no computers to solve this. Indeed, even if we had computers, how do we actually solve this particular equation was still a somewhat open question, even as late as about 20 years ago. Only now do we have good tools and good techniques to solve it numerically, but we'll see that several lectures from now. So what Professor Harold M. Westergaard, that's his full name, I believe he's somewhere from the Nordic countries, hence the last name Westergaard. So Professor H.M. Westergaard in 1926, he actually published a paper, and you'll see this cover of that paper in the next slide. He published a paper where for the first time ever, he derived analytical solutions for these equations. Now, that was not his last paper, obviously. Subsequently, he published some more papers where he applied some corrections and some variations to those solutions. But to this date, about 100 years after this paper is published, and 1926, so 2026 will make it 100 years, it's not that far away. About 100 years since this particular paper was published, this equation, Westergaard solutions, are still the most celebrated set of analytical solutions for rigid pavements. It is still used very widely, and only recently in India and other countries have we moved away from these into more modern methods. So just a little bit background, because it's in our engineering classes we learn a lot about these solutions. I don't think we learn enough about the people behind these solutions. And back in those days, 100 years ago, everybody was a polymath, everybody was a polyglot. So someone who had a significant contribution in one area tended to have significant contributions in other areas also. And such was also the case with Professor H.M. Westergaard. So he was actually a professor of civil engineering at the University of Illinois in Urbana-Champaign. He started his position there in 1920. That also happens to be my alma mater, so I also did my PhD there. So I'm proud to have some amount of connection to that. In addition to providing solutions for JPCP, which is what we're going to talk about in this class, he's actually very well known for analyzing any type of slabs and concrete in general. So he was very good at manipulating these equations of the Sophie-Germain equation for plate theory and trying to find different solutions under different conditions. In particular, he has also studied beams and slabs. So you'll find some solutions for beams also from Westergaard. And most interestingly, he's also known in fracture mechanics. So very famous problem that he's known for is if we actually have a plate and we have a hole in that plate, then and we apply some amount of loading, for example, some kind of compression or tension on this, then what is the stress distribution around the hole? This was also one of the famous problems that he provided the first set of analytical solutions for. So he was famous for a large number of things, but as far as this set of lectures goes, we are mostly concerned with his contribution to plate theory for jointed plane concrete pavements. So as I said, in 1926, he published a very celebrated paper that provided the first set of analytical solutions for JPCP pavements using those equations. And this is a screenshot of the paper. It's, by the way, it's over 100 years old. It's actually out of copyright right now, so you can actually download it and look at it yourself. It's a very well written, and papers back then, literally the physical product paper was at a premium back then. So papers tended to be compact, they tended to be well written. Philosophy has changed over time. That's not how papers are written today. But the title was very, very simple and pretty straightforward. Computation of stresses in concrete roads. So first of all, he's saying concrete. And he's saying roads. What he basically means, the terminology was not used back then, but this is basically JPCP. So he showed he derived method for computation of stresses. As we shall see, he actually also computed the deflections. So not only did he calculate stresses, he also gave us formulas for calculating deflections. Those are not as useful as the stress formulas, but they are there. So the paper gave us solutions for computation of stresses in concrete roads. This was published in 1926 by the Highway Research Board, which today, for those of you who are a little bit deeper in transportation engineering, you might know that as an American agency called the Transportation Research Board, which till today is probably the very best in the world in terms of conducting research relevant to pavement engineering and transportation engineering. So anyway, I picked up one screenshot from this particular paper because I thought this is actually the very first equation in that paper, and I picked it up because it's quite interesting when you read it, and it gives you some insight to what we just talked about in the earlier part of today's lecture. So he writes as follows: a certain quantity, a certain quantity. So he's not ascribing any special behavior to that quantity, it's just a particular quantity. A certain quantity, which is a measure of the stiffness of the slab relative to that in the subgrade, occurs repeatedly in the analysis. So even before he sets out his solutions and sets out his analysis, he's giving you a preamble and telling you that there is a certain quantity which is some sort of a measure of the relative stiffness of the slab to that of the subgrade. It is of the nature of a linear dimension. Note this term dimension. So this is not some magical term which has come out of nowhere. It simply came out of dimensional analysis, which is what we did in the beginning of today's lecture. So it is of the nature of a linear dimension, like, for example, the radius of gyration. So it was just purely as an example, the idea of calling it a radius came to his mind because it's also like a length term. It will be called the radius of relative stiffness. So Professor Westergaard actually came up with the term radius of relative stiffness. And again, it is relative stiffness because it's a relative stiffness between the plate and the subgrade. And he called it radius because he just thought that it's a length. Length sounds like a radius, so he decided to call it radius of relative stiffness. Maybe in a parallel universe, somewhere they'll call it length of relative stiffness. Maybe. But in our analysis today, this name has continued 100 years later, and it's the radius of relative stiffness. He gave the symbol L, which is still the symbol we use to this date, and it is expressed by this formula. You will note this is identical to what we saw last time. The only difference is for Poisson ratio, he uses mu. That is what they do in the US and North America. In Europe and in India, we tend to use this nu, this other Greek letter, as a symbol. So with that one exception in notation, this particular formula, which Professor Westergaard put as the very first equation to his very celebrated paper, in today's lecture in the beginning, I just showed you how to derive it by simple dimensional analysis of the Sophie-Germain equation with the correction for this coefficient of subgrade reaction. So as you can see that this term, the radius of relative stiffness, not a magical term, not a term that came out of nowhere. It just came out of dimensional analysis. And because it was used again and again in the solutions. When we look at certain solutions, you see it's all over the place. You have to calculate it and use it in multiple places. Because of that, he just decided to give it a special symbol. And that continues 100 years later to this date. So now that we've gotten over the preliminaries in this very first equation in the paper, let's jump right into the particular solutions. So what exactly did Westergaard do? Westergaard made the following case. For infinite plates, and I'll qualify this infinite plates in a second. For infinite plates on grade, so we're looking at a slab on grade situation here. For infinite plates on grade with circular loading, that was one assumption. Now, when we say circular loading, then what are the characteristics of a circle? Well, the radius, to which the symbol is A, and the loading, of course, has some amount of load P. So it is some load P, which is distributed over a circle, what we call the footprint of the load. It is distributed over a circular footprint of radius A. For this particular condition, Westergaard derived a series of analytical solutions. Now, I should add, getting the analytical solutions for a fourth order equation or biharmonic equation is not easy. It is actually done using something called Airy stress function. And we're not going to go into those derivations in this class. It's not really important. But the basic process by which this is done is that you have the fourth order equation, and then mathematicians come up with a whole bunch of possible solutions. So there are handbooks full of possible solutions for these. Each of the solutions are going to satisfy some boundary conditions. So they satisfy, of course, the biharmonic equation, and they satisfy certain boundary conditions. And then you look back and you think, okay, my problem has these boundary conditions. Which of these solutions that mathematicians have come up with satisfy these boundary conditions? I find the best solution which satisfies the biharmonic equation but also satisfies the boundary conditions which represent my problem. Combine those two together, and that's how you get the solution for your problem. So it's not that we start from the problem and then systematically derive the solution. In practice with these Airy stress function, what happens is that we look up a series of solutions which mathematicians have derived and try to find the best solution which suits our case. So what are the cases that we're particularly looking for? Westergaard solved or provided analytical solutions to the equation for three particular loading cases: interior loading, edge loading and corner loading. In interior loading, when we talk about interior loading, the basic assumption is that the load is in the middle of the plate, and the plate has an infinite dimension, which I've highlighted here. It has an infinite dimension, which is just to say that the joints are very far away from our load. So that's what interior loading means. Corner loading, obviously in corner loading, we have a joint. That's why we have a corner. But we assume that the other joints are very far away. That's why we call this an infinite plate. And for edge loading, first of all, what Westergaard assumes is that the edge loading is actually a semicircle. This diagram, by the way, is taken exactly from his original paper. So he assumes that the loading is actually semicircular. So half the load is on one slab, half the load is on the next slab. For this semicircular loading, he assumes then that, of course, we have this one edge over here since we are on the joint, but the three remaining joints are very far away. That's why in his own paper, he's drawn the joints using these squiggly lines just to represent that they are very far away. For each of these cases, Westergaard gave us the solution for stress and he gave us the solution for displacement. Now, but the question is, which stress? Recall that I mentioned that in a plate, at any given cross-section, we have the neutral plane. At the neutral plane, the stress is zero. We're going to have some stress above that, and we will have an equal but opposite direction, opposite sign stress below that. So if we have a tensile stress at the top, we will have a corresponding and equal amount of compressive stress at the bottom. We are actually concerned with tensile stresses. In the sense, at any particular location, which might be defined by some x or y coordinate, at any particular location, not only do we want to know the magnitude of the stress, we would also like to know whether the stress is on the top surface or on the bottom surface. Why are we interested in tensile stress and not compressive stress? Simply because the tensile strength of concrete is much greater than the compressive strength of concrete. As a simple rule of thumb, the tensile strength of concrete might be between 4 to 5 megapascal. We saw this about 2 lectures ago. Whereas the compressive strength can easily be 1,000 times of this. Which means if failure is going to happen, it is first going to happen in tension rather than in compression. So that's why Westergaard was particularly interested in calculating the tensile stresses. What he found was that when you have corner loading, which he called case 1, when you have corner loading, so you can imagine it that the slab is actually loaded at the corner and you have a load over here and the slab is going to bend like this. It's going to look somewhat like a cantilever, but it is not a cantilever, but it's going to look somewhat like a cantilever. And if you recall from your classes in structure analysis, a cantilever will have tension at the top surface. So that's why Westergaard said is that tension is, which we call sigma C over here, C for corner, is going to be at the top for corner loading. Coming to interior loading, so interior loading is going to look something like this, and where you're going to have tension at the bottom. It's going to look somewhat like a simply supported beam, but it is not a simply supported beam. I'm just giving you an analogy. In a simply supported beam, perhaps you recall, tension is at the bottom, which is why he writes here this sigma I, the interior loading, which is case 2. So this is sigma I and this is sigma C. For the interior loading, the tension is at the bottom. And for edge loading, he found, even for edge loading, it's closer there to this case, this closer to the simply supported case than it is to the cantilever case. Even here, this sigma E, which is the critical tensile stress at the edge, this is also at the bottom. So not only did Westergaard give us solutions for the tension, for the stress, he actually told us which side the stress, whether top or bottom face, which side the stress is going to be tensile, and then his equations help us calculate those values. One thing to keep in mind, the notation here, tension is positive. I pointed this out in an earlier slide also. Tension is positive. That was a sign convention which he adopted, which we are also going to continue to use. So if we end up getting a negative tension, that basically means compression. We don't have to worry about compressive stresses. Positive tension means tension, and we have to be concerned about tension when we get it. So for each of these loading cases, let's look at the solutions that Westergaard gave. They are actually relatively simple. They're simple enough that you can just pick up a calculator and do the calculations. So the first case was corner load, which he then showed with the subscript C. So he gave us a formula for sigma C, which is stress at the corner. He also gave delta C, which is the displacement at the corner. And here, let's look at each of the solutions. So for sigma C, he gave this solution. This is 3p over h square, 1 minus some term called A1 divided by L. This L, I remind you, is again that radius of relative stiffness. So it's fourth power of EH cube divided by 12k into 1 minus nu square. This is fourth root of. Don't forget this fourth root over here. So this is the radius of relative stiffness raised to the power of 0.6. What is A1? Recall that A, as is shown in the diagram over here, this is the radius of the loading. A1 is simply A into square root of 2. This seems odd. Where is the square root of 2 coming from? It's actually coming from a stress consideration. That what you are not actually interested in A, you are interested in the distance of this corner to the center. And so we know that if this length is going to be A, this length is going to be A, which is the radius, and this length is also A, which is shown over here. So this hypotenuse is going to be A into square root of 2. That's where this A1, A into square root of 2 is coming from. And then for delta C, here again, you have this A1 over L into some constants. You will note here that here it's P divided by KL square, where K is the coefficient of subgrade reaction and L again is the radius of relative stiffness. So K is coming up over here. When we do a solved example, which we'll do after looking at the formulas, when we do a solved example, we will see that we have to be quite careful with the units in this case. The most common error students tend to make for these problems is getting the units wrong. So we will look at that when we do a solved example. Okay, coming to Westergaard's interior loading. For interior loading then, he gave us sigma I and delta I, two sets of formulas. And for sigma I, it is reasonably more complicated than last time, but not significantly more complicated. What he found was that this sigma I, first of all, consists of some P over H square. So that is in common with what we had for corner loading. And this is the logarithm, this is ln, so this is the natural logarithm. So when you're doing the calculation for your calculator, please check that you're using natural logarithm. So this is the natural logarithm of L, radius of relative stiffness, divided by some term B plus some constant. B, he gave us two definitions for B, and this is again coming from considerations of stress, considerations of shear stress. B is equal to A when the radius is significantly large, when it's greater than 1.724 times of H. And B is then this expression, note this is raised to the power of 0.5, so this is actually a square root. So it's equal to this particular expression when A is small. So this is one calculation. So even before we start calculating the sigma I, we first have to establish what is B, for which we have to check these two conditions. We will do that in the solved example, which I'll show you once I go through the formulas. And then for delta I, you'll see B is curiously not there. We go back to using A. L is, of course, still there as expected. And here again, K and L make a comeback. So we do have K over here. And as I pointed out, we have to be very careful with the units in this case. And the last set of solutions which Westergaard provided was for edge loading, which is in this case. Note, in the case of edge loading, we do have a semicircular load. In the next lecture, which I'll get to, I'll see that there are some updated solutions where instead of semicircular load, you can also have a circular load. We'll talk about that when we get to it. Okay, here he's given us sigma E. Now, what you'll immediately notice is that it's a pretty long formula in this case. That's true. But most of it is just simple constants. So we have a 1.84 here, which is a constant. 4 nu over 3, 1 minus nu over 2. These are just constants. These are relatively simple to calculate. As we'll see in our solved example, if you do this systematically and calculate it term by term, it makes the entire calculation relatively easy. Here again, we have some P divided by H square. But in this case, we do have this extra term, ln of EH cube 100 Ka power 4. So K is here making a comeback in sigma E. And then for delta E, it's here again, we have some A over L. But here we do have P into the square root of this particular term. 2 plus 1.2 nu divided by EH cube into K. So in this case, K makes a comeback here. So you don't have to memorize these formulas for Westergaard's equation. They are fairly complicated and there's no point memorizing them. What you should know is how to calculate them systematically. They are simple formulas in the sense that you can pick up a calculator or you can do it in a spreadsheet. They are also complicated formulas in the sense you have a lot of terms and you have to make sure that equations, etc. are consistent. So the key to solving any problem using Westergaard solutions is to do it systematically. And that's why after this slide, I will go through an example where we will systematically solve a particular problem using Westergaard's equations. And I'll show you then how to avoid making some typical mistakes. Now, before then, we have to ask ourselves a question. Of these three loading conditions, that is corner loading, interior loading, and edge loading, of these three conditions, which one is critical? The one which has the highest tensile stress, everything else being the same, that is the thickness being the same, the slab being the same, the load being the same, when all else is equal, whichever of these conditions happens to give us the highest amount of tensile stress, that is the critical condition. And interestingly, we'll also see this in our solved example. It turns out that the edge stress actually is the critical stress. So among sigma C, sigma I, and sigma E actually gives you the highest amount of stress. The important thing to note there is, if I consider this interior loading, in interior loading, the assumption is that the joints are very far away from the load. So there's no effect of the joints. This is actually fairly close to layered elastic analysis. So if I have an interior loading condition, which I can solve using Westergaard solutions, or I can solve using layered elastic analysis, which we use for flexible pavements, you can try solving this. It's not particularly difficult. What you will see is that the solutions are not very different from each other. They are comparable in terms of the stresses. But for edge, which is now when we actually have a joint and the load is placed over here, the remaining joints, etc., are far away, but we do have this one joint and the load is placed over here. What we find is that in this case, you cannot use layered elastic analysis. Layered elastic analysis does not allow you to put a joint. But the presence of this joint and this edge stress condition actually leads to the highest magnitude of stress. What that goes to show is layered elastic analysis cannot be used for rigid pavements, because if you use layered elastic analysis, that is the equivalent of considering all loading to be interior loading, whereas as Westergaard showed, and as which we'll show in our next example in the next couple of slides, the edge loading actually gives us the maximum stress. So if you want to consider the critical stress, which is the maximum stress, maximum tensile stress, we do have to use this particular theory, the Sophie-Germain equation, and with the subgrade correction, we do have to consider this particular theory with solutions, at least the ones provided by Westergaard, if not better solutions, which we'll talk about in the next lecture. All right, so let's do a solved example. So primarily in this solved example, I'm not going to do all the calculations. I do expect all of you to pull out your calculators later, copy the example, use the slides, but please do the calculations yourself. You can use a calculator, you can use a spreadsheet, but unless you actually sit and physically do the mathematics, you're not actually going to follow. In the lecture, on the other hand, I'm not going to do all the mathematics. I'm going to show you the key aspects of the mathematics where students typically make mistakes. So let's look at the problem. Consider a wheel carrying a load of 20 kilonewtons under a pressure, this is a tire pressure, of 1 megapascals. The wheel runs over a JPCP slab whose thickness is 200 mm. So we're given H is equal to 200. And we are given that P is equal to 20 kilonewtons. We are not given A. That's something to keep in mind. We are given the pressure. So we will calculate it, but keep in mind we are not given A. Now, this JPCP slab of H 200 mm, it's sitting on top of a subgrade whose K value is 50 megapascals per meter. Now, I had, for given K is equal to 50 MPa per meter. Now, I had pointed out when we talked about the lecture on material properties, this is an interesting unit. Another way to write megapascals per meter is Newton per square millimeter per meter. So we have both millimeter and meter in the same units. That's a source of common confusion. We first of all have to ensure that we are accounting for this problem. Okay, the question is calculate the maximum tensile stresses and deflections when the load is placed at interior, corner, and edge. And then among these three, calculate which stress is the highest. So basically, we are asked to go through Westergaard solutions and comment on the relative magnitude of the three stresses which we'll calculate out of it. Now, before you solve this problem, the first thing you have to establish is what system of units do you want to use. Now, generally, as all of you have learned, the system of units that you may generally want to use is kilogram, meters, seconds, so mass, length, and time. In civil engineering, however, it is better if you use what's called the force time convention. That is force length convention, So this is what we call MLT, mass length time. In civil engineering, it's much better to use an FLT convention, which is the force, length, and time convention. So in this case, time is going to be in seconds, but it doesn't actually matter because our solution is static. So we don't have any time units anywhere in our solutions. What we have to choose units of force and we have to choose units of length. It's an arbitrary choice. You can choose whatever units you want. But perhaps the easiest set of units to use for all problems is that you use force in terms of newtons and you choose length in terms of millimeters. Note our units, the actual units of our problem don't follow this convention. And the units which I've given here are actually the conventional units which are used. So generally, load for traffic loads is shown in kilonewtons. The slab modulus is shown in, so the subgrade modulus is shown in megapascals per meter. The thickness is shown in millimeters. None of this is wrong. But what we want is, in this problem, we want to convert our problem to a uniform system of units so that we don't make any errors in unit conversion. And that uniform system that we choose, it can be whatever you want, but what you should use, in my experience, which is the best system, is to use newtons and millimeters. So with that in mind, let's do a couple of calculations. First of all, I mentioned we do not know the radius of our footprint. So footprint is basically, if this is my slab and I'm seeing it in profile, and this is my tire load on it, then what Westergaard assumes, it's an assumption, but what Westergaard assumes is that this footprint of the tire on the slab, so if I'm looking at now in elevation, this footprint is actually a circle. So we are given that P is equal to 20 kilonewtons. And now I just said that we need to choose a uniform system of units. So let's rewrite P as 20,000 newtons. So we'll do our calculations using 20,000 newtons for the load. We have to calculate the radius. We are given the pressure. This is small p, or actually just for ease, let me write this as Q. So we are given the pressure is equal to 1 megapascal. And this is 1 Newton per square millimeter. I'm sure you know this unit conversion. What is the relationship between area and pressure? I hope all of you remember this, that load is equal to pressure into area. The area of a circle is pi a square. And so if I want to calculate A is going to be the square root of P divided by Q into pi. P is 20,000 over here. Q is going to be 1. Pi is 3.1415. Don't substitute 3.1415, whether it's your calculator or it's Excel. Just use the value of pi which the calculator or Excel will provide. Let the internal calculations do it to whatever number of decimal places. Computers generally go to 16 decimal places, so don't lose accuracy in rounding off. I have done that calculation here in this slide. So 20,000 divided by square root of pi into 1. What we get is that A in millimeters, very important, turns out to be 79.8 millimeters. You could write this as 80 mm, but generally my recommendation is don't do any additional rounding off. So if you decide to keep it to a precision of 1 decimal point, stick to that. So don't round this off to 80 unnecessarily. So don't do more rounding off than is strictly required. And if you're using a spreadsheet, let the spreadsheet round off to 16 decimal places. You need not do it. So what we get is A is 79.8 millimeters. Okay, that's fine. The next question to ask is calculate the radius of relative stiffness. Now the radius of relative stiffness was the fourth root of EH cubed divided by 12k into 1 minus nu square. We are given K is equal to 50, and let me write the units like this, Newton per mm square meter. Now, mm and meter are mixed units. As I said, we want to express all our lengths in millimeters. So I'm simply going to rewrite this meters as 10 power 3 millimeters. So what this is actually going to be, 50 into 10 power minus 3 Newton per cubic mm. That's going to be a value of K. So keep this unit conversion. It's very, very common for students to forget to do the unit conversion for K. So K is 50 into 10 power minus 3 or 0.05 if you want to write that way, Newton per cubic millimeter. Now, we still need, H is given as 200 millimeters, so no unit problems over there. What about E and nu? Let's go back to the problem, and the problem doesn't tell us what value of E and nu to use. This is where you want to recall our lecture which we had on materials for rigid pavements. If you don't know the value of E and nu, you still can look, you know that it's made of concrete. So we know that concrete has some typical values. So what are the typical values for E and nu? We saw that the typical value for E is 30 gigapascals. Now this is gigapascals. We want to use Newton and millimeters. So I'm going to write this as 30,000 Newton per square millimeter. 30,000 megapascal, 30,000 Newton per square millimeter. So I'm now keeping my unit consistent. Nu for concrete generally will take as 0.15. You can also take 0.2 or 0.25 might be okay. But generally, if you don't know anything better, we just take 0.15. So now for my calculation of E I assumed as 30,000, note the units. H is 200 mm, so there's no problem with units over there. 0.15 for nu, and then for K, I took 50 into 10 to the power of minus 3. I put these values in. Again, I'm not going to do the mathematics, but I encourage all of you to definitely do the mathematics. Don't just assume that my answers are correct. You'll get around 799.8 millimeters. One thing I want you to notice is look at the relative magnitude of this. So if somebody asks you what is approximately a reasonable value for radius of relative stiffness without providing any further information, what they're actually asking you is it of the order of 10 mm? Is it order of the 100 mm? Is it order of 1000 mm? So when somebody is asking you radius of relative stiffness approximately, they're just asking you what is the order of it in millimeters. You should know that it's of the order of a couple of 100 millimeters. It can also be around 1000 millimeters. So roughly maybe 5000 to 1000 millimeters is a reasonable value of radius of relative stiffness. In this particular example, it so happens to be 799.8 millimeters. Now, I definitely encourage all of you to do this calculation yourself, because in subsequent lectures also, we're going to keep calculating and using the radius of relative stiffness. So as Westergaard said about 100 years ago, it's a pretty important term that keeps coming up again and again. It's still true today. It's still true in a lot of our analysis. So make sure that you have expertise and you have some practice in calculating this particular value. And keep in mind, when you look at the answer, and for some reason, if you're getting 10 millimeters or if you're getting 10,000 millimeters, understand you made a calculation mistake somewhere. And typically that unit conversion is the most common source of calculation error. Okay, so now that we've done those preliminaries, we've calculated L and we've calculated A. Now we can calculate the actual value of stress and displacement. So we have corner loading. This was a formula for corner loading. We had A is equal to, if I go back 2 slides, I had A is equal to 79.8 mm. So A1 is going to be equal to 79.8 into square root of 2. Again, please do this with a calculator. Don't write square root of 2 is 1.414. You're just going to make some unnecessary round off approximations. Do it on a spreadsheet, do it on a calculator, use a large number of significant digits. Okay, so A1 is equal to A into square root of 2. So you can calculate this. So this is simply going to be 79.8 square root of 2 divided by 799.8 raised to the power of 0.6. You can calculate this term. P here, use newtons and millimeters. So this is going to be 20,000, 3 into 20,000 divided by 200 square. That's 200 millimeters square. A over L doesn't have any units. If P is in newtons and H is in millimeters, the final unit of the solution is going to be in Newton per mm square, which is megapascal. That's exactly what we want. Now, let's look at delta C. P again is going to be in 20,000 newtons, so we are still using newtons. K is going to be in Newton per cubic mm, right? Because you have to do that conversion, it's going to be 5 into 10 power minus 3 Newton per cubic mm, which again, I did their entire derivation over here. All right, so what I have here is I've got some Newton divided by Newton per cubic mm, and L is also going to be in mm, so this is L square, this is going to be mm square, Newton cancels out, this is 3, and so I'm going to get the solution in mm. So if I follow this formula and I use this consistent unit of equations, then I'm going to get the solution, it's consistent system of units, then I'm going to get the solution in millimeters. I have done that substitution over here. So I did a quick calculation that A1 is equal to around 102.8. But again, in your calculator or in your spreadsheet, don't round this off. Let the calculations continue to a large number of significant digits. So I put those values over here. Here, as I mentioned last time, I have 3 into 20,000 divided by 200 square. I get the answer as 1.04 megapascals. So for corner loading, my stress works out to 1.04 megapascals. Similarly, for delta C, I go through all the calculations and I get 0.61 mm. Note here again, this is smaller than 1 mm, and that's generally the case. The displacement for this small amount of loading will be of the order of 1 mm. You can measure it, but you can't actually see it when it's happening. That was for corner loading. Case 2 in Westergaard's theory was for interior loading. So here we have this. In interior loading, the first thing we have to check is we have to compare A to this particular value. So what we have here is A we are given as 79.8, H millimeters. H was 200. I think without even doing the calculation, you will agree with me that 79.8 is less than 200 into 1.724. So this condition is not going to be valid. This condition, on the other hand, is going to be valid, which means we have to calculate this particular term B. You can go ahead and calculate it. Again, make sure that all the units are in millimeters. And here again, P is going to be 20,000. H is going to be in millimeters, so it's 200 square. L is in millimeters, B is going to be in millimeters. What you want to do in practice when you're doing these calculations, do it systematically. Calculate ln of L over B first, then add it to this term first. Calculate this term separately. So once you've calculated this, and once you've calculated this, then systematically calculate 3 into 1 plus 2. Do it systematically. Don't put the entire expression into your calculator or your spreadsheet. You're going to make a mistake. And similarly, for delta I, calculate these individual values systematically. So calculate this, which I can call 1 first, multiply it by 1 over 2 pi first. Multiply that by A over L square first. Get this whole thing, which I can call 2. Add 1 to it and then add 1 over here, and then let's call this value as 3. So what you want to do is you want to calculate 3 into 1 plus 2. So systematically break up the equation into smaller pieces. Calculate those for smaller pieces and then perform the necessary operations on it. Do not try to evaluate the whole expression at once. You will almost certainly make a mistake when you do that. Anyway, I've gone ahead and done the calculation. You can verify the numbers that I've plugged in over here. What we will find is that delta I in this case is 0.77 megapascals. Sorry, that's sigma I. And delta I works out to, this is supposed to be 0.08 mm. So pretty small, if you recall. We'll compare the values in a second. But now coming to edge loading, basically the same formula. I'm not going to repeat this, but again, there are many terms over here. Please evaluate the terms one by one and then perform the necessary operations. Don't try to evaluate the entire expression at one go. Okay. I did the substitution, so you can just check if the values are fine. The stress comes out to 1.62 and the displacement comes out to 0.25. So to summarize, I put this together in this table where for each location, I've just summarized what is the critical tensile stress and what is the displacement. What the interesting thing to see is the stress is lowest at the interior and the stress is highest at the edge. That's exactly what Westergaard also said. The stress is going to be highest at the edge. What we find is that the displacement actually ends up being highest at the corner. And that is particularly important when we talk about pumping. So recall that when we had a discussion on pumping was basically caused when we had a displacement and the slab is being displaced downwards. That's creating pore pressure. That's pushing the water upwards. So this fact is actually quite important when we talk about pumping. But for today's class, we're basically concerned about stress. So the maximum stress we verify is indeed happening at the edge. Furthermore, recall, as I said, the flexural strength is around 4 to 5 megapascals, let's say 4.5 megapascals, just as one number. If I take the stress ratio is the stress to flexural strength. I get a ratio of 0.36, which is quite less than 1. That is an important typical behavior of JPCP pavements. The stress ratio, SR, which is sigma over FCR, this is typically going to be less than 1. It is typically going to be significantly less than 1. That is an important characteristic, which will then become important when we start talking about fatigue theory later on in our analysis. But for now, I just wanted to point this out. Okay, so what we did in today's class is I introduced to you this very important term, radius of relative stiffness, and then I showed you what were Westergaard's original solutions from his 1926 work to calculate these. I went through a solved example where I calculated each of these terms. Again, I encourage you to please do the entire calculation yourself. Don't assume you'll be able to do it without practice. In the calculation, there are two important tips to keep in mind. One, unit consistency. Generally, try to use newtons and millimeters for force and length, respectively. Express all the given values in newtons and millimeters. That's one tip. And the second tip is there are many terms in Westergaard's equation. It can be quite a long equation. Calculate each term separately, simplify it systematically. Don't try to evaluate the entire expression at once. Most of the time, students who do that make a mistake, and there's a good chance you too will make a mistake if you do that. So don't do that. Now, Westergaard's equations were derived in 1926, almost 100 years ago. As you can probably imagine, a lot has changed since then. So, in the next lecture, I'm going to talk to you about some updated solutions. There have been subsequent researchers who've provided better solutions for Westergaard's equation, Westergaard solutions. And in the next lecture, we're going to see some of those solutions. We're going to solve an example problem, and then we're going to compare those solutions with Westergaard solutions and comment on it. Thank you. I'll see you in the next lecture.